Hello and welcome on today's video. My name is Wouter Peere and I'm the founder and main developer of GHEtool Cloud. And today I want to talk with you about the MuoviELLIPSE, the latest innovative product from Muovitech that has been released today in GHEtool Cloud. So let's get started. The MuoviELLIPSE is, as the name suggests, not a circular but an elliptical heat exchanger. And just like the turbo collector, it has internal fins which rotate clockwise and counterclockwise when you move through the pipe. And the idea behind these internal fins is that it enhances the turbulence so that your heat transfer becomes better even at lower flow rates. Now, this video will have some similarity to the way the model for the turbo collector was developed. So in case you have not watched that video, please do so, it's linked in the description below. Now, if we want to model this MuoviELLIPSE, we need to consider a couple of things. Namely, because we have internal fins, we know that heat transfer and the fluid behavior will be different from a traditional smooth circular pipe. And the way we are going to solve this is by using computational fluid dynamics, CFD, and more specifically, DNS or direct numerical simulation. And this is the same type of study, the same type of simulation that was done for the turbo collector, and it is based on the work of Nicholas Hittman. But this only solves the problem or the heat transfer inside the pipe itself, the fluid behavior, let's say. But we also have an irregular shape, and to take that into account, the irregular elliptical geometry, we use something which is called the boundary element method. And this methodology was inspired and co-developed by Professor Massimo Cimino. So let us get started with the first part and then go over to the boundary element method. But before we jump into the computational fluid dynamics, let us recap again what is the Reynolds number and why do we care about it. Now, when we're talking about fluid behavior, the Reynolds number is an important number because it tells us when a fluid is laminar and when it is turbulent. Now, a laminar fluid is typically when your flow rate is rather low, your fluid is moving slowly, and you can imagine that all the droplets are moving in parallel with each other. And this means that the droplets in the middle, they have a very hard time transferring the heat to the pipe wall, which is why a laminar flow rate, although having a low pressure drop, is not so good for heat transfer. Whereas if you have a higher flow rate and your droplets are rushing through the pipe, they tumble over each other, and once in a while every droplet would touch the wall, and it's easier to transfer heat in that way. And that's a turbulent flow range. And between the laminar and the turbulent flow range, there is this transition zone in which the fluid is neither 100% laminar nor 100% turbulent. And the onset of this transient zone is typically around 2300 for smooth pipes. And the philosophy is that with these internal fins, as we also saw with the turbo collector, this transition starts already sooner because the fins enhance local unsteadiness in the flow, causing already some turbulence before this 2300. But the question is, how can you quantify it? And to quantify that, we need CFD. Now, computational fluid dynamics, as we said before, is used all over engineering. And we use it to design airplanes, racing cars, but also chemical plants to see how certain flows interact and mix with each other. And there are different ways of modeling in computational fluid dynamics, but the one we are interested in is direct numerical simulation. And with DNS, what we actually do is we solve the Navier-Stokes equation, the equation on how a fluid behaves, to very, very small time and spatial scales. And we do that so that we can fully get all the information of the turbulence, because the fins inside these pipes are rather small. So we also need a rather small spatial scale to see when the turbulence starts, and doing that come up with the correlations needed to get the pressure drop and also the heat transfer for these type of pipes. Now, just to recap what was done for the turbo collector, because it's rather similar to what has been done for the MuoviELLIPSE, is basically Nicholas created a 3D model of this probe and put a flow through it with a rather high Reynolds number so that it's always turbulent. And that you can see here on top, it's a beautifully hellish blue, almost cyan blue. And then the flow rate was lowered in different steps. And the lower the Reynolds number becomes, you see the 2300, the turbulence is not everywhere, it's transient. There are some regions where there is turbulence, some where there is not. And this goes down until 1800. And here you still can clearly see some transient behavior, some local turbulence. But in 1700, it's fully laminar. You can clearly see the different color layers, the different fluid layers. So there is no turbulence here whatsoever. And the idea is that by going from a high flow rate towards a lower flow rate, that we find the threshold at which the turbulence starts, to see how the internal fins actually affect the heat transfer inside the pipe. And when this was done for the MuoviELLIPSE, these were actually the results. So on the left, we have the results for the friction factor. Now, the friction factor tells us something about the pressure drop. And as you can see, it was compared to a smooth elliptical probe. And you can see that at 1850, the elliptical probe with these fins in it, the MuoviELLIPSE, it deviated and already becomes turbulent sooner. And then when it's turbulent across the 2300, it follows the well-known equation, the Haaland equation for the friction factor in turbulent flows. Now on the right side, we have the Nusselt number. Now the Nusselt number tells us something about how good the convective heat transfer is. So we typically want a very high Nusselt number because we want a very good heat transfer from our fluid to our pipe. And also here you see that at 1850, there's a sudden jump. So the heat transfer increases significantly because this induced turbulence. And then after 2300, it again follows the known pattern for the heat transfer or the Nusselt number in smooth pipes. So this was what we wanted to say about the heat transfer inside the pipe, everything related to the fluid. But now let's discuss the heat transfer outside. And typically, in geothermal design, you have circular probes. A single, double, coaxial, whatever, all are circular. And the advantage is that when you have a circular shape, we know analytical solutions for the heat transfer. But for elliptical and other irregular shapes, we do not know that. So in order to find the effective borehole thermal resistance, we need to rely on numerical methods instead. And one of these numerical methods is actually the boundary elements method. Now, without going too much in detail, basically what it does is it's a numerical method for solving linear partial differential equations like the heat transfer equations in our case. So if you think about it, the borehole, if you take a cross section, you have two ellipses in it, and the heat transfer is of course two-dimensional. It's from one pipe to the other and from the pipe to the borehole wall and so forth. And what this boundary element method does is, instead of solving that for the whole area, the whole two-dimensional problem, is basically reformulating the equations to equations that work on the boundary of the objects. So the pipe, elliptical boundaries, as well as the borehole circumference. And by doing so, what we can actually do is model the exact geometry of the pipe and get the accurate borehole resistance for that. Now, as you can imagine, this boundary element method is not really fast. In GHEtool, we need quite a lot of borehole resistances when we do a simulation because we have variable fluid properties, flow rate, etc. We already discussed that. And therefore, what we do is we use this physical model, this boundary element method, and we train an artificial neural network with that. Now, artificial neural networks, it's part of the big AI terminology. We already have a video on this topic. It's also linked in the description. But basically, what we do is we train an artificial neural network based on this very detailed numerical calculations to have a very fast and accurate model to actually solve the heat transfer inside the borehole for the MuoviELLIPSE. And just to show how the boundary element method looks like a little bit, you can see it here. And so we have a borehole with two elliptical probes inside, and you can see that each line it has certain dots. These are the nodes for which the heat transfer is actually solved. And as you can see, each node also has two arrows, and one tangent to the object and one perpendicular to it. And these are the two vectors that play a role in handling the numerical equations. And so they both play a role in the heat transfer, let's say. So that's a little bit how you need to think about the boundary element method. Now, given our correlations now from the CFD simulations, given this methodology are these results for the heat transfer inside the pipe and inside the borehole, let us take a look at the effective borehole thermal resistance. And this is given here for a borehole with a length of 100 meters, a grout of 1.5 watt per meter Kelvin. We see here the MuoviELLIPSE, a DN45, and as a reference also a smooth pipe, DN45. And what you can see is that the onset of turbulence, the sudden jump in borehole resistance, it occurs sooner for the MuoviELLIPSE than for the smooth pipe. And that's because of these fins, they induce turbulence sooner at 1850 Reynolds instead of 2300. So that's really clear here. But also when we go towards higher flow rates, we see that both solutions, both probes have almost the same effective borehole thermal resistance. In fact, the smooth pipe is even slightly better. And the reason for that, or to understand that, we have to take a look at the cross-sectional areas. Because both here have a diameter of 120 millimeter. But what you can see for the smooth TN45, these pipes are actually ever so slightly closer to the borehole wall. And of course, if you're already turbulent and your heat transfer is really good, this contribution of the grout resistance, heat transfer to the grout, becomes more and more dominant or important for the calculation of your borehole resistance. And since our circular geometry is just closer to the wall, also the borehole resistance is just slightly better. But the whole philosophy or the whole reason why the MuoviELLIPSE was actually developed is because due to the elliptical shape, it's easier to install these probes in slightly smaller boreholes. So when the same comparison is done, but now using a DN90, a 90 millimeter borehole for the MuoviELLIPSE, you see that the transition to turbulence, it still happens at the same instance, the same flow rate, but now the borehole resistance is lower for every flow rate, basically due to the smaller borehole diameter. Because if the borehole diameter is smaller, there is less grout resistance and the heat transfer also is easier. Now this was for the thermal aspects. And when we talk about the hydraulic counterpart, we see that the increase in pressure drop for the MuoviELLIPSE starts a little bit sooner. And that's because the same story was told for the turbo collector. We have this turbulence already somewhat sooner at 1850 Reynolds number, but we pay for that with extra pressure drop. So that's why the increase in pressure drops already starts sooner. But also we see that over the whole flow rate, basically, the pressure drop for the MuoviELLIPSE is higher than for the reference or the equivalent smooth circular pipe. And the reason for that lies in a difference in hydraulic diameter. Now, the diameter of a circular pipe is easy to understand, but for irregular configurations or irregular shapes like an ellipse, it's not straightforward. And the concept of the hydraulic diameter is used to find an equivalent diameter for a circular pipe that more or less has the same thermodynamic or fluid dynamic behavior as the irregular shape. And this hydraulic diameter is defined as 4 times the cross-sectional area of the pipe divided by the wetted parameter. So the parameter around this area. And since for an elliptical probe, and the area versus parameter ratio is just slightly smaller, also our hydraulic diameter is slightly smaller, meaning that our velocity is slightly higher, which increases in turn the pressure drop. And that's why the pressure drop of the MuoviELLIPSE, an elliptical probe, basically with the same diameter as a regular probe, has a slightly higher pressure drop. Now, this was what I wanted to say about the models. As said, they are, as of today, available in GHEtool Cloud. If you go over to your borehole resistance tab, you can find them in a list ranging from DN32 to DN63. Please give it a go. I'm really curious to hear your thoughts on these probes. I hope you found this video interesting. Please consider subscribing, sharing, or liking this video, and I'm looking forward to seeing you in our next video. Take care.